Hello everyone, welcome to Electronics Tutorials. In this video, I am going to discuss on the topic half-wave rectifier with a resistive load. Let me start with the definition for a rectifier. A device that converts alternating current to direct current is called a rectifier. So, what is a half-wave rectifier? A half-wave rectifier is a device that converts alternating current to direct current only in one of the half cycles of the input supply. It can be either the positive half cycle or the negative half cycle of the input supply. Also, since it converts one form of energy, that is AC, to another form, that is DC, it is also referred to as a AC to DC power converter. Let us start with the analysis. Here in figure 1, I have shown the circuit diagram for a half-wave rectifier with a resistive load. The circuit consists of a transformer with a primary voltage of Vp and a secondary voltage of Vs equal to Vm sin omega t. We have a diode connected to the upper path of the secondary of the transformer in the way that is shown here. As I already have said, I will be considering a resistive load here. Let the voltage across the diode be represented as Vd and the voltage across the output be represented as V0. I0 here forms the output current. Please note the input voltage is alternating current, that is AC, and the output we are expecting is direct current, that is DC. I will be explaining the working of this circuit in the positive and negative half cycles of the input supply separately. In figure 2 here, I have shown the circuit equivalent during the positive half cycle of the input supply. In the positive half cycle of the input supply, the diode is forward biased because the anode of the diode is connected to the positive terminal of the secondary and cathode is connected to the negative. Once it is closed, the current I0 starts to flow across the load in the direction that is shown here. Since we have assumed a lossless diode, the output voltage V0 is equal to the input voltage Vs. Further, let us also assume the direction of the current shown here as the positive current direction across the load. So, in the positive half cycle of the input supply, both the output voltage as well as the output current are positive. Let us now look at the waveforms for the positive half cycle of the input. Here, the first set of waveforms is the input voltage, which is our sinusoidal or simply alternating current. Let the peak value of the input voltage be denoted by Vm. Since we have assumed an ideal diode, the output voltage V0 during the positive half cycle of the input supply will simply follow the input voltage, which is Vs. That is why in the second waveform shown here, that is for the output voltage, the waveform across the period 0 to pi is exactly the same as that of the input voltage between the same duration. Further, since we have assumed a resistive load here, the output current will be in phase with the output voltage and will have a peak value equal to Vm divided by R. The waveform shown in blue color here represents the output current I0. The third waveform shown here is the voltage across the diode itself. Since we have assumed an ideal diode, the voltage across the diode between 0 to pi will be 0 volts itself. This is the waveform analysis for the positive half cycle of the input supply. Let us now go back and analyze the circuit during the negative half cycle of the input supply. Figure 3 shown here represents the equivalent circuit during the negative half cycle of the input supply. During the negative half cycle of the input supply, the upper branch of the secondary of the transformer will have negative voltage and the lower branch will have positive voltage. Therefore, the diode anode will be at a negative potential compared to its cathode. This means the diode is now open circuited because of the voltage across its anode and cathode. Since the diode is now open circuited, the load is disconnected from the supply and therefore the load voltage V0 is equal to 0. Further, since there is no connection between the secondary of the transformer and the load, the output current I0 is also equal to 0. Therefore, during the negative half cycle of the input supply, the output voltage and output current are both 0. Let us now look at the waveforms for the negative half cycle of the input supply. Now, I will be analyzing the waveforms between the period pi and 2 pi. Coming to the second waveform here, which is for the output voltage, you can see that the output voltage is 0 because the diode is now reverse biased. The output current will also be 0 during this period. Coming to the waveform for the diode voltage, we will now note that the input voltage, which is the negative half cycle of the input supply, is applied across the anode and cathode terminals of the diode, and since the diode is reverse biased, the voltage across the diode is equal to the input voltage between the duration pi and 2 pi. That is why between pi and 2 pi across the third waveform here, we have shown the same exact input voltage across the diode as well. Right. This is the analysis of the waveforms for a half wave rectifier during the positive and negative half cycles of the input supply. It should be noted that during the positive half cycle of the input supply, the diode conducts and therefore the output voltage and output current are both positive. On the other hand, during the negative half cycle of the input supply, the diode is reverse biased and therefore the output voltage and output current are both 0. Let us now move on towards the mathematical analysis of this circuit. The average output voltage of the half wave rectifier is equal to the DC component V0 and is given by V0 equal to 1 divided by 2 pi integral 0 to pi V0 omega t d omega t. Let me explain how this equation is formulated. If you come back to the waveform for the output voltage shown here, we will note that during the negative half cycle, the output voltage is 0. So, when I am trying to find the average value of the output voltage, I need to take the period between 0 to 2 pi. However, since the output voltage is 0 between pi to 2 pi, I have taken the integral limits only between 0 to pi. Further, as I previously explained, during the positive half cycle of the input supply, the output voltage is equal to input voltage, assuming a lossless diode. Therefore, when I write the equation for the DC component V0, it is given by 1 divided by 2 pi, where 2 pi is the period of the overall operation, integral 0 to pi, because during the negative half cycle output is 0. What we are integrating is the output voltage, which is V0 omega t d omega t. Since the output voltage is equal to input voltage during 0 to pi, in the next step, I will write it as 1 divided by 2 pi integral 0 to pi Vm sin omega t d omega t. Please note, I have replaced V0 omega t by Vm sin omega t because the output voltage is equal to input voltage between the interval 0 to pi. Vm is constant here, so I will take it outside the integral and I will apply integration to sin omega t. Integration of sin omega t is minus cos omega t multiplied by the coefficient of omega t. Therefore, this equation reduces to 1 divided by 2 pi into Vm followed by integration of sin omega t, which is equals to minus cos omega t over the limits 0 and pi. I will take this minus symbol outside, so this will become minus Vm divided by 2 pi multiplied by, let us now apply the limits over cos omega t, so it will be cos pi minus of cos 0. In the next step, that is here, I have written minus Vm by 2 pi as it is, cos pi is equal to minus 1 and cos 0 is equal to 1. So, this will be minus 1 minus 1. This will reduce into minus Vm by 2 pi into minus 2. So this simplifies to V naught equal to Vm divided by pi. This is the value of the average output voltage for a half wave rectifier. Moving on, the average output current of the half wave rectifier is equal to the DC component I naught and is given by I naught equal to V naught divided by the load resistance R. In my previous equation, I have found the value for V naught and is equal to Vm by pi. Let us apply the same in place of V naught here, and therefore the average output current will be Vm divided by pi R. Let me now continue to the RMS value of the output voltage. The equation for RMS value of output voltage is given by 1 divided by 2 pi integral 0 to pi V naught square omega t d omega t whole to the power 1 by 2. Let us now substitute V naught as Vm sin omega t. So the equation reduces to 1 divided by 2 pi integral 0 to pi Vm sin omega t whole square d omega t whole to the power 1 by 2. I'll apply the square here. So this will become Vm square multiplied by sin square omega t. Other values are retained in the equation. I will take Vm square towards the constant side. So this will become Vm square divided by 2 pi multiplied by integral 0 to pi sin square omega t. However, sin square omega t cannot be directly integrated. So I will write sin square omega t as 1 minus cos 2 omega t divided by 2. The rest of the elements of the equation are retained as it is. Now I will take this 2 to this point here. Therefore, in my next equation, the constant term would be Vm square divided by 4 pi. Following that, we have integral 0 to pi d omega t minus integral 0 to pi cos 2 omega t d omega t whole to the power 1 by 2. Looking into the first part of the integration here, integral of 0 to pi d omega t is nothing but omega t, and then we have the limits 0 and pi. Coming to the second term, the integration of cos 2 omega t is equal to sin 2 omega t divided by 2, and then we have the limits 0 and pi. Let us now apply the limits. For omega t, it will be pi minus 0, which is written here. For the second term, it would be sin 2 pi minus of sin 0 whole divided by 2, which is written here. In the next step, we have Vm square divided by 4 pi multiplied by pi minus 0 retained as it is minus of sin 2 pi is 0 minus sin 0 is also 0. So I have written 0 and 0 here. So after simplifying the contents of the curly braces here, what we obtain at the end is just pi. Therefore, the final expression for the RMS value of the output voltage will be Vm divided by 2. Moving on, let us now write an equation for the output RMS current, and it is given by Vrms divided by the load resistance R. Vrms is nothing but Vm by 2, which is our previous expression. So after substituting that in place of Vrms here, we obtain the output RMS current as Vm divided by 2R. Moving on, the average power produced by the input supply is Pi equal to Vs into Is, where Vs is the RMS value of the input voltage and Is is the RMS value of the input current. The average power absorbed by the load is given by P output equals to Vrms multiplied by Irms. So, the power factor of the circuit is given by Pf equal to Vrms multiplied by Irms divided by Vs into Is. This is the expression for the power factor of the half wave rectifier. Moving on, let us now find the value for the ripple factor of the half wave rectifier. Please note, ripple factor determines how well a rectifier converts AC voltage to DC voltage, and it is given by the formula Rf stands for ripple factor equals to square root of Vrms divided by V naught whole square minus 1. Previously, we derived Vrms as Vm divided by 2 and V0 as Vm divided by pi. Substitute these values here and it will simplify to pi divided by 2. Computing this, you will obtain the ripple factor for the half wave rectifier to be 1.211. The next parameter I will be considering here is the efficiency of the rectifier, which is also known as the rectification ratio. The rectification ratio is the ratio of the output DC power to the input AC power. It is represented by eta and is given by PDC divided by PAC. PDC can also be written as I0 square divided by R, and in a very similar fashion we have PAC as IRMS square divided by R. So this will simplify to I0 square divided by IRMS square. We have previously found the values for I0 as well as IRMS, and these values are substituted in this particular step. After simplifying, you will obtain the rectification efficiency to be 4 divided by pi square, which simplifies to 0.40528 or simply 40.528%. Please note, this is the maximum achievable rectification ratio for the half wave rectifier. Let us now move on and discuss the form factor. Form factor is a measure of the shape of the output voltage and is given by the expression FF, which stands for form factor, equal to Vrms divided by V0. Vrms is nothing but Vm by 2 and V0 is equals to Vm by pi. So this simplifies to 1.5707. And the last parameter I will be considering here is the transformer utilization factor. The transformer utilization factor TUF of a rectifier circuit is defined as the ratio of the DC power available at the load resistor to the AC rating of the secondary coil of the transformer. So TUF is given by PDC divided by Vs into Is. Right. That is about the mathematical analysis of the half wave rectifier. Let us now move on and discuss the applications of the half wave rectifier. It should be noted that half wave rectifier is commonly used in signal modulation applications, rectification applications, signal peak applications, and is also used in triggering or firing circuits. And lastly, it is used along with either the step up or the step down transformers to achieve a desired value of the output voltage. Lastly, let me now very briefly discuss the advantages and disadvantages of the half wave rectifier. I'd like to start with advantages first. The first and foremost important advantage of a half wave rectifier is its simplicity. In simple words, it has the lowest number of components available and therefore is quite simple to construct. The second advantage is it is cheaper upfront cost. That is, it requires less equipment. However, it should be noted that there is a higher cost over time due to increased power losses by the rectifier circuit. Let us now move on to disadvantages. A half wave rectifier only allows one half cycle of the input supply to the load. This leads to a power loss. Coming to the second disadvantage, we note that half wave rectifiers produce a very low output voltage. Lastly, the output current that is obtained by the half wave rectifier is not purely direct current, and therefore it contains a lot of ripple. In fact, we have already seen that it has a very high ripple factor. These are the advantages and disadvantages of a half wave rectifier. Well, with that we come to the end of this video. In my next video, I'll be reconsidering the half wave rectifier but with a inductive load. If you found this video to be informative, kindly like and share this video and subscribe to my channel for more information on electronic devices. Thank you for watching. Have a good day.